You post the grade?
I forgot to make it visible.
Okay, so we're still hiding, so it's normal you haven't seen it.
Sorry about that.
All right. Okay, so you want to do it first, or
Yeah.
I mean, give it back maybe at the end of the class. Yeah. Okay. All right. Okay, so let's first talk about the content we need to cover, and then I'll leave some for homework as a reading homework, right? So then we spend some time talk about the exam. All right. Okay, so last chapter we wrap up torsion, right? So far we cover if you have a structure, a long sling bar, right? If you have axial load, we call it what? A bar, right? Or a cable. That's what we call it. But if you apply a moment at the end, applying a torque, and then we call it a shaft. It's basically a long bar, you're applying torque at the end. Okay. Now, this chapter, we are going to look at another type of deformation. That is when you have a long bar, and now you're applying a lateral load. Right? So as I show here, so the load now is not along the axial direction. It's still a force, but it's a lateral. It's perpendicular to the axial direction. Right? Okay, so we all have this life experience. If you apply load to the side, what happens? Things will bend, right? So therefore, we're going to talk about bending. All right? And in this kind of structure, we call it a beam. Right? So it's the same, can be the same bar. If we apply load laterally, then we call it a beam. So that's more like a model, a physical model, we call it. Once you realize, if I say a beam, you know, okay, this structure must be under lateral load. The load is perpendicular to the direction. Okay. All right. So for the beam, right, it's actually things get really complicated. Right. One thing is the beam can be complicated. All right. And also the load. For example, like I show here, this one you have a beam. This we call a beam, right? So because the load is perpendicular. So this beam, you can have a force applying there. But possibly you can also have a moment. So you can have a moment applying there. You try to apply a pair force, try to twist it, right? So like what you always do when you have a wire, right? You apply force to try to bend it, a moment, try to bend it. So that can be another type of load, right? And also you put a lot of weight on it, right? There are so many cars on top of a beam. So you have like a distributed load. So things get complicated, right? So we're going to talk about there are three things, okay? The first three is there are three types of support you can have for a beam, for the end. How are you going to support a beam, fix a beam, right? To fix it to a wall, right? That's one way, as I show here. So this one we call fixed end. So you can fix something to a wall, right? So like this one, okay, so like this one here, right, fixed to the end. So that's a beam. We call it a fixed end. So that's one type. Another type is I can put it there, but put a joint there. So this can move freely. So like here, right? So if I can, I cannot remove it. So this one here, this point here, this connection, we call a pin support, right? A joint. Actually, we had this last chapter, right? So we talk about you have a rigid beam, and there is a pin, and it can move around, but cannot move away. We call that a pin support. So here the same again. So we call it a pin support. Right? Another type will be you can have one end that's free, right? Like I just showed here, this picture. For example, the left end is pretty much free, right? So you can have a free end, or you can have a fixed end, or you can have a pinned end. Any other possibility? Any other possibility? You see in life, you know, when you have a bar, somehow one end can fix different way, another end fix another different ways. Any other type of fixation you see when you connect a bar to something? Yeah, I said the pin here, right? So the pin is which one? Here in the middle. What do we show here? Okay, so pin is, let me just draw it here. So you have this part. So this point, and then you have here. So this connect to the wall, right? It's like a hinge there, right? The hinge supported, and then you can move it around, rotate, like what I just showed you here, but not necessarily can move away. So that's what we call a pin support, right? Okay, so that's one pin support, and then fixed support. That's you just like the bottom one. You stick something to the wall, I mean to the floor or to a wall. There, it's all a fixed support, right? Okay. Any other possible support? Actually, we still say more than just the three types here. Yeah. Yeah, you can put a wire here. For example, like this one. You can, for example, you can add a spring, right? It's like a wire to the wall. That provides some resistance, not totally free. Actually, in many cases, they are not totally free. There's some resistance, right? It just oftentimes we can ignore this resistance to the rotation. So that's a pin support. But this is possible. You can have a spring, a rotation spring. What else? Any other possible restriction you have seen? What about if you have something that can move around but cannot rotate? Does that exist? Yeah, something like a slider, right? You can slide, move a little bit, but not necessarily rotate. Okay, so we can draw this way. For example, you have this end here, right? So you can have a slider, something like this. But your wall is going this way, right? So you can move a little bit, but because there are many, let's say you put a few wheels here, and then this thing can slide up or down. So this left side is a wall. The right side is a beam. So you can slide up or down a little bit, but you can never rotate. So that actually exists. And if you look through the homework problems, there are actually homework related to that. Okay. But that, I would say, is not our focus, so won't be in the exam, I can tell you. So the basic three types are the three ones typed in here. So the fixed end, the pinned end, or can be a ruler support. Okay. Actually, not the ruler support, or the free. So it can be a free, what? So it can be a free end. Right. So that's the three basic types most common. So the ruler, the one draw here, that's not the one that's common. So we won't put that in the exam anyway. All right, so that's how you fix a beam to the wall or to the support part. Okay, there's three types, main types, or you can say four types actually we show here, right? Okay, then because it's different restriction, so the end you can fix it different ways. So therefore, we're going to talk about three types of beams. All right. So one is we call simple beam. That is both ends are pin. So pin. So you have we call it a simple beam. Another one is free, fixed. We call that the cantilever beam. So I'll just draw it here. The second one, maybe I'll draw on this side. So the beam is like this. Okay. So this stick to the wall. But on this end is free. So you have a load, or you can have a different type of load there. So one side free, one side fixed to the wall. So that's a cantilever beam. All right. What other combination? You can also have fixed, right? So you have a wall here, and you can have another end fixed, right? So fixed, right? And this one is an indeterminate beam, so we're not just talking about it for now. We'll leave it later, right? Okay, other combinations. You can also have a beam, right? So you pin support here, but this end like fixed, one pin, right? That's also possible. And you see this kind of structure, right? This one is also indeterminate, so we'll leave that later too, all right? So the other one we may have is you have pin here, and then pin in the middle. Then this end is free. So this one we call overhanging beam because this part stick out hanging there, right? And this one is determinate. So we're going to have three basic determinate beams Basic three types. So one is a simple beam, one is a cantilever beam, one is an overhanging beam. So for now, we'll just focus on these three type of beams. All right. And this one is so this will be indeterminate. Right? This will be indeterminate. We'll leave it to a later chapter to talk about it. Right? So now you see we're going to have indeterminate structure again. So we're going to use the Fed.com again. Right? So we're going to use it multiple times, the Fed.com approach. All right. Okay, so three type of beams. All right. And then the load. Okay, actually this picture already showed. I think I have a next slide there showing the load. Okay, so there are different type of load you can apply to the beam, as I mentioned earlier. You can have a force applying there, you can have a moment applying there, or you can have a distributed load applying there, distributed force. Of course, you can also have distributed moment applying there, right? So there really actually can be four type of a load there. Our focus will be the three type: the force, concentrated moment, or distributed force. Right? Okay. Now the force can actually apply in arbitrary direction, like I show here. Right? But we'll be only talk about force like this one, perpendicular. Okay, why? Because whenever you have a force in any arbitrary direction, you can always divide it into an axial direction force and a perpendicular, right? When you talk about the axial direction force, we already talked about that, chapter 2, right? When you have a force that apply axially, we know it's going to be an elongation or compression. So we already know what kind of deformation, stress. So therefore, we don't need to consider that component. Therefore, we only consider the perpendicular one. So the standard load format will be like here. So you can have a distributed load, that's distributed forces, right? We use the letter Q represented. Or you can have a concentric force, we use P represented. Or you can have a concentric moment, like M here. So we're going to talk about three type of boundary conditions, three type of loads, and also three type of beams. All right. So simple beam, cantilever beam, and overhanging beam. And naturally, we'll focus more on the simple beam and the cantilever beam. All right. Okay, so that's the situation may occur for a beam. Right? You can have this complicated load, complicated boundary conditions, right? So you can see now beams are much more complicated than a bar or a shaft. And that's why actually for the beams, we're going to have four chapters talk about it. So instead of one chapter, we're going to have 4 chapters. We talk about the simple beam, the load first, then we talk about the stress, then we talk about deformation, then we talk about indeterminate beam. So we have 4 chapters all for beams. So you'll see beams are more complicated. All right. Okay, so this chapter will start with the load. All right. Okay, so the load, as I said, we are going to focus on you applying concentric force, moment, or distribute load. So we talk about this 3. Okay, now let's use one example, just get the idea why these things, the load be so complicated, you need a chapter to talk about it. Okay, let's say we have a beam, like what I show here, the top picture. Okay, what kind of beam is this one first? Cantilever beam, right? One in the free, one in the fixed. So that's a cantilever beam. You know, like a board, right? When people are diving, the board, so that's a cantilever beam, right? Okay, when you sit down on the chair, actually the chairs are a cantilever beam, right? You can treat it as a cantilever beam. Right. Okay, now in this beam, let's start with one very simple situation. We just have one load P applying on this side. Okay, so the question will be, if I apply a load to a beam, what kind of internal force or maybe moment I'm going to have in this beam? Right. Okay, I ask this question because let's say if I have a bar, okay, this is a bar here. Okay, now the force applying here. What kind of internal force you have in a bar? You can cut it here, right? Then you draw the free body diagram, P here, and this will be the N. So we know there will be only one force, internal force applying there. The N we call normal force or internal force, right? So this N will equal to P based on equilibrium. Okay. Now, what about this situation? If you have a beam, the force is applying this way. What if I cut, let's say I cut it here. Randomly, I cut the location. Right? Okay, cut it here. Then what kind of force are you going to have at that cross-section? Okay, you say shear, right? So like you show here. This is a free body diagram. So there may be shear, and there may be movement. Okay, there may be also force in this direction, right? But I can prove it's 0. Because I'm talking about the lateral force. The force, load P is perpendicular. So sigma Fx equals 0. Immediately say this N will be equal 0. So I'm not consider the N there. Because N, if there is N, in real life, you will see N and P combined together. But we know if there's N, we already deal with it in chapter 2. We can use the equation from there. Right? Okay, so later on, we don't talk about N anymore. So this will be gone. All right? So now you may have a shear force V here, and you may have a moment. Okay. Now, can this structure be in equilibrium? Or can I find out what's the force here, V here, and what's the moment here? Okay, yes, how? Equilibrium, right? So equation of equilibrium, all right? So equation of equilibrium. Okay, now equation of equilibrium. First, sigma Fx equals 0. See, this is the x direction, right? Okay, it's gone, automatically satisfied. So with that equation, we don't need it here anymore for the beam. So we're going to need sigma Fy equals 0. Okay, in this situation, what's sigma Fy equals 0? This is the y direction, right? So you have P minus V equals 0. In other words, V equals P. Oh, I know the internal. If you cut there, inside this beam, there's going to be a shear force, V, equal to the load P in this case. Right? Okay, now what about the other one? Movement, M. Sigma M, movement to somewhere need to be 0. Or should it be 0, right? Anywhere, actually. So pick one spot. Point A, point, we call this one B, so point C. Point A, okay, let's say sigma M to A equals 0. Okay, now translate this equation. To all to A equals 0. So you're going to have V times X minus this M, right? Equals 0. Okay, that means M equals to Vx. Okay, what's V? P, so equals Px. All right. So if you cut anywhere in this cantilever beam that is subject to a load at the end, you're going to have two things, two internal forces. One is actually the internal shear force, V. Another is the internal moment. Right? This is the moment, that's the interaction between the two sides of the surface. So we call it internal moment. Right? So you're going to have a moment and a shear force. And this shear force, we know it's equal to P. And the moment is equal to Px. Okay, now things get strange now. This M now is what? Depend on the location. Right? Because if I cut at 1 meter here, or I cut at 2 meters, two different locations, you're going to have different movement. Right? So movement now become a variable. Or internal load now become a variable. And it keeps changing. So that's why now the things internal load become complicated. And that's why actually we need a chapter to talk about it. And this is a very simple situation. Just one load P applying there. Right? So things get complicated. So the one thing we need to set up is, in general, when you talk about the beam, okay, so the V will be a function of location. Moment will be a function of location. Right? So you're going to have internally, you're going to have two reaction terms. One is the internal force, one is the internal movement. Right? And that two things going to be depend on locations. Okay. So therefore, when we try to talk about the beam, you need to say, oh, the moment is going to change everywhere. This shear force may change everywhere. right? So you need to find out what, how it change, right? How the V change and how the moment change, and then you find out where is the maximum, and that may be the location things going to break. If a beam break, it's going to break at where the load is maximum, right? For example, for this beam, okay, now we know this equation, right? So if you plot this movement to, let's say this is the x direction, right? If I plot this as a maybe I just draw a different location. Okay, let's say I just draw it here. Okay, so this is the moment. If I draw with the location x, okay, so it's going to be at here is 0, and then gradually it'll be change. So it'll be this equation. It's a linear equation because px, right? P times x. So you have a p is like the slope. So you go up this way. So now the moment will be maximum here. We know, we say it can be increasing, right? So if this bar is going to break, where most likely it's going to break first? Where you connect to the wall, right? Not the center, to the wall, because that's where movement is maximum. Inside, you know, if you are the particles, imagine the particles inside the material feel more tension, more stress, more load there at the end. So most likely crack going to start there, right? Okay, so next chapter we're going to talk about stress. But here, just give you a general impression that, okay, this is a variable. It's changing. Movement is changing. So our task for this chapter is figure out for any beam under any type of load, how do you determine the V and the M at any location? How does it change? Can you plot it? How it change? And then find out the maximum. That will be the task for this one. Okay. Now, how to find it? How did we find it here? You make a cut, right? And then you draw the free body diagram. It will show up, then you write the equation about it, and then you find what's it equal to. Right? You can do this cut anywhere. But so if you cut at any arbitrary location x, then this will you'll find the general expression related to x. So you know everywhere. Right? So you can plot. Once you have this function, say m equals px, then you can plot it anywhere. Any point you can find the value. Right? So the general approach is make a cut, then write the equation about it, and find out the relation, and then you can plot it. Okay, so that's our first approach. Then later on, we're going to simplify the process, have some rules you can directly draw without doing this process. But first, let's do this way, see if we can go through one more example. All right. Okay, so before we do that, here is the sign convention. Okay, so this is something you need to remember it or kind of memorize it. Okay, or at least you need to understand it, right? Okay, so now again, what's a positive movement? What's a negative movement? Okay, here I'm talking about internal movement. The M and the V we find out from the cutting. Okay, so what's a positive movement? Depend on deformation, right? Remember in this class, we define positive, negative, always depend on deformation, right? If you stretch a bar, elongation, so this pair of force we call positive. Although they are pointing or different direction, they're positive. Okay, that's a positive pair. Now for movement, okay, we define a positive pair of movement as if you are bending things upward, right? So if you're bending something upward, if you're bending this way, okay, that's a positive pair of movement, right? As shown here, this is a positive pair of movement. Okay, opposite, vice versa. So if you're bending things down, that's a negative pair of movement. All right. So again, now you see on this surface, this is a positive movement going this way. On this surface, this is a positive movement. Right? So they are opposite direction, but they both called positive. So now it's important. You go look at this way, or you go look at this way. All right. So the positive definition spatially will be different. Right. So the fundamental rule is how it deforms. Yeah.
It's not a positive moment, it's a positive deformation.
It's a positive deformation. Therefore, this is a positive pair of movement. So this movement we call it positive. All right. Okay. So this is actually easier. Then the hardest one is for the shear force. Okay, here's the positive. So if you generate, what do you call this way? Clockwise, right? Clockwise deformation, that's positive. Vice versa, if you generate the counterclockwise twist, that's a negative. Okay, so quickly, let's go back here. Okay, for this one, the shear force V equals P. Is this positive or negative? It's positive, right? So on this side, if we point downward, it's positive. On this side, if point upward, it's positive because it generates this clockwise twist, so it's positive. So they're all positive. Now for the moment, if you look at this one here, this one equal to px, right? You try to bend things upward, so this is a positive. It's a positive deformation. Okay. Now if you look at this one, positive or negative? It's positive. So this one and this one, there are action reaction, so they both positive. Where are red negative? Okay. Remember, we define a positive moment for deformation. Now, when you write the equation of equilibrium, now some old stuff you learn in statics, you always assume one direction is positive, other will be negative. So for equation of equilibrium, you define spatially one direction is positive, then the opposite will be negative.
You assume counterclockwise as negative.
In the equation of equilibrium, yes. But in the deformation, there's no clockwise or counterclockwise issue. It just you deform bending upward or bending downward. So this parallel thing. Okay, look at this one again. This will help you understand it. Okay, this n here, we say it's positive because this generated elongation, right? Okay, but when you write the equation of equilibrium, you write negative n plus p equals 0. So you say n is negative. Because when you write the equation of equilibrium, you give a direction that's positive. Everything against it negative. Yeah.
I would elaborate and just remind everyone to be careful. You're not talking about the moment, you're talking about the deformation. It's different.
Yes. In this class, we always define positive and negative based on deformation. Right. Yeah.
Are we ignoring weight in this case?
Yeah, most of the time we ignore the weight. Yes, in all the homework problems or exam problems or in class, we just ignore the weight. Unless specially say you have to include the weight. Actually, now I can ask you to include the weight because weight is what? Like a distributed load. You have here a little bit, right? Everywhere constant. So that's like a distributed load. So we actually can include the weight now. Right? All right? Okay, let's quickly maybe go over one example. This one we just went over. Let's try a different example. Let me see if I have a different one. Okay, this one. Okay, so for this one, let's say if we can find out the moment somewhere. Let's say I want to find out the moment here in this location. Can we find the moment? How do you find the moment or shear force, the V and the M inside here? What's the approach? First, make a cut. You have to make a cut to make it show up, right? Okay, so I make a cut here. All right, so I can draw this part of the beam. So here's a pin. Now this is the object I select. Now this is not a complete free body diagram. So I need to label all the forces, right? So here's a V I'm looking for. And here's the M I'm looking for, right? At location X. Right? Let's say this is location X here. Okay, now is this complete? Reaction. So I have reaction here. Okay, so to be able to find out the V and M, what I need? I need RA. Now, can you find out RA? Yes, you can use the whole thing. So RA, this will be RB, right? So RB, can you find it? Yes, based on equation of equilibrium. Okay, you do that, so you'll find RA, RB. Now let's say this is known. So if this force is, let's say 20, what's RA here? You can do the equation of equilibrium, right? You'll find out this will be 10. Okay, so I skip this step. You will do it afterward. Okay, now can I find out V? Yes. So sigma Fy equals 0. Use the equation of equilibrium, right? So I have Ra minus V equals 0. So therefore, V equals Ra equals 10. All right. Now, can I find out the M? Sigma moment to any point, to A equals 0. Okay, so what? So it will be V times distance x, right? This is the x distance. Okay, then minus M equals 0, right? Okay, so M equals to what? Vx. Oh, so that equals to 10x. So now I know I found out V and M at any x location, right? Okay, so you're, yes?
You make that first cut, are you just taking a guess as to which way put V and which way put M?
Yes. Before I solve it, I don't know which way V is supposed to be, right? So I just assume it's positive. And positive is supposed to be this way, right? So I always assume positive. Then if I find the value is negative, that means just go opposite.
Okay, so let's say you found a negative number, would we go ahead and box that negative number as our answer, or would you want to fix the free body diagram and flip that arrow?
You can do either way. You can just say, okay, I found the V equals negative 10. So therefore the V will be opposite direction. Or I just say V equals negative 10. Based on the sign convention, I'll understand what's V equals negative 10. Right? Okay. All right, so here's another homework assignment for you. Okay, find out what's the VM here. All right, we'll talk about that next time. So I want to stop here, leave some time so we can talk about the exam. All right. Okay, so we have the exam here. All right. So based on previous experience and the issues that came up along, so here's what I'm going to do. So I'll give you all the exam back. So we'll call your name, and if you don't have any issue with it, you can just take it home. All right. But if you think you may have some issue there, don't take it out of this room. You need to return to me, then come to me during office hours, or Tuesday, Travis will be available during noon time. I may still also be around, so you can come to the office. We can talk about the issues. If there are any dispute about the grade, I mean, right? So if you take it home, then I will basically make no change anymore. All right.
Is there anyone in here in the online section? Okay, are any of y'all going to want to take your test home? If so, come up here.